to adhere to it unless there was a collision guarantee before they can actually, wait for for that particular collision to be cleared before they can actually forward their frame. So that's what made the one minus persistent CSMA very, very selfish. Okay. So there had to be a better way to address that. And that's where the probability comes in. The probability persistent came in. And the probability persistent was designed to compromise the attempt to reduce collision that the non-persistents had to reduce idle time, and also the one minus persistent also had in terms of selfishness. And the rules were pretty simple, but very robust. If the medium was idle, you will transmit with probability time and delay one time on one time unit with a probability of 1 minus probability. Now this time unit is typically equal to the maximum propagation time. But to go back to propagation time in datacom 1, you understand that it's a period within which a signal is designed to propagate. So that was then it's based on metrics of how much data it's been transmitted, the size of the data, as well as the medium speed or the medium rating. Like for instance, this a bandwidth. Is it a 10 meg bandwidth, 20 meg, 2 meg, whatever it is? With the data size can determine the probability or the propagation delay. Okay, so assuming you carry maybe a 1 gig data and you transmit over maybe a 2 meg bandwidth pipe or medium, then you could calculate your propagation time delay and then forward it to all the various other stations so they know how much time a given station that's transmitting that particular 1 gig data on that particular medium will take before they can actually forward the information. So that way you in an effective way, a station could easily know when to transmit and when not to, because now they can easily sense and calculate propagation time delays. Okay, and we allocated time slots as well, obviously as part of it from non-persistent, And if the medium is busy, you continue to listen, blah, 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 until the channel was very idle before you could transmit. If not, you just repeat your process all over again. Now, if transmission is delayed, one-time unit always have to repeat the process by going back to step 1. And that's where you basically know when to transmit, because now you have an ideal medium, so you can forward information. The question that comes up is, what is an effective value of P propagation? What is an effective value? Because assuming that you had somebody downloaded maybe 1 terabyte data, do you expect the other stations to wait on that particular medium for that 1 terabyte to be cleared before? So the question here is, what is an effective propagation time? Because we can allow one station to basically hog the medium, it just wouldn't be effective. So in that case, you could probably switch to a different channel. If you had multiple channels on a particular medium, then it would be ideal to switch to a different channel that was less congested or was ideal. Then you could forward. Then you could allow that station to forward their frames on that particular channel. Okay. So the question, as we pointed out, is what was an effective P? An effective P, in a sense, if you want to assume an end station's waiting to transmit while a transmission is taking place, then at the end of the transmission, the expected number of stations attempting to transmit uh, would happen to be the number of stations, or would happen to be the number uh, that would be allocated to a particular station ready to transmit within a given time of probability. Okay, so if you had maybe a number of station times probability time and happens to be greater than one, then on the average there will be a collision if it's greater than one. And then when that happens, you have to repeat the attempt over and over again until you guarantee more or less transmission of collision expected. Once that happens, you can retry to compete with new transmissions from other stations. And eventually, when all stations try to send continuous collisions and zero throughput, then you have the option to make use of your probability time. So in a sense, the value of P will be determined by a value that's less than 1. If it's more than 1, which is your station number times the probability, if it's greater than 1, then there are bound to be issues. But if it's were to be less than 1, then you could basically know an ideal time to uh, send a particular given frame. Okay, so in a sense, NP, which is the number of station multiplied by the probability, should always be less than 1 to actually get a peak propagation time or the effective propagation time. There are drawbacks within a setup and implementation. Okay, so as I was pointing, it has to be less. If it's greater than 1, you're going to have collision. But if it's less than 1 or less than NP, then you're going to have a good way to transmit without collision. The drawback with that is that if heavy loads are expected, then P should probably be small in such a way that NP would be less than 1. However, if P were to be made smaller, stations must wait longer. That's where the delay comes in to attempt transmission, which obviously results in long delays. So essentially, creative ways to handle carrier sense multiple assets. But obviously, all of these were just part of the early implementations. But today, they are much more effective and efficient designs to address probability times and what have you within the carrier sense. Today, the most efficient solution for high-speed max schemes and Ethernet happens to be carrier sense multiple assets with collision detection, which we'll look at very quickly. So the solution was to come up with a CSMA with CD or collision detection. So as we were pointing earlier on, the problem with CSMA was collision occurs within mediums for duration of frames transmission, which wasn't good for long frames. So to address that issue, collision detection was added, where stations listens for a transmission. If collision is detected, they stop transmission immediately. And the rules of that was only wait for the medium to be idle before you transmit. Otherwise, you move on to step 2, kind of like moving on through a loop, you know. If the medium is busy, you continue to listen until the channel's idle. Okay, so if the medium itself is busy, you continue to listen until the channel's idle. So now you listen to both the medium and then the channel. So that's one key thing to put in mind with the carrier sense multiple access. With collision detection, you are both basically monitoring or sensing at the medium level itself as well as the channel. And if both were idle, then you could transmit. Or in a sense, if you were to apply the rule with lanes as an illustration, then you say that before a car gets onto a particular road, they first have to actually examine the entire road itself first to make sure there are no cars, moving on it, and also observe a particular lane that they want to get on to see if it was idle. So in this case, there are two ways to avoid accidents within a particular road as a driver or as a motorist. You always have to watch out for the road itself. It's kind of like the way we always do when we're driving. Before you get onto a highway or a road or whatever, which has got, maybe one or two or three lanes, you first, kind of like scan the entire road first. Make sure, traffic situation are not crazy. And then you also monitor for the lane that you want to get into to make sure that lane is not what occupied, which is your channel here. So in this case, the road itself is the medium, and the channel will be your what? Your lanes. And within the carrier sense, multiple assets with collision detection, you have to observe a driver or a patient have to observe these two or sense these two uh, mediums and channels before they can actually transmit. And if there's a collision, if happens that collision happens, in a way, regardless of, as I pointed earlier on, regardless of how efficient road signs have been introduced on a particular road, there's always bound to be an accident at some point in time, you know? So in this scenario with these the collision detection on that carrier sense, if a collision is detected during transmission, transmit a brief jamming signal. The station must transmit a brief jamming signal to assure that all stations know that there has been a collision and they can sense that transmission so they can cease their transmissions. So it's a collision, you make sure you send a jamming signal, and every device, every station that wants to get that wants to transmit would have to uh, acknowledge that and cease their transmission. After transmitting the jamming signal, you wait for a random amount of time first, preferably call or in the technical term called the back off. So the jamming signal for the waiting period is considered a back off. Okay, so the jamming signal to wait for a random amount of time is considered a back off before they can actually attempt to transmit again by repeating the process from step one. And then once that is done, collisions are issues of collisions were heavily addressed or significantly improved. Okay? Collisions are caused usually when two adapters transmit at the same time, even though they sense a collision based on different voltages. So usually, if you're dealing with electronic devices, voltage fluctuation can even create problems. So usually within the CD of the carrier sense, collision is usually detected when two adapters transmit at the same time, and adapters sense are based on voltage fluctuation or voltage differences. Okay, so keep that in mind. So if a voltage fluctuation of a particular electronic device of a given station, adapter of a given station is fluctuated in the voltages, then you could have issues with collisions. And both lines can be found very idle, and both you'll have to wait for a busy line to be what? Idle again before they can retransmit information. Okay, so here's a scenario that detects how CSMA slash CD operation occurs. So at a given time zero, A transmits, C transmits. Signal on buses, obviously, C and A. At time one, A's transmission and, and C's transmissions cease each other. So A's transmission realizes that, hey, C's transmission is just bumped into me or has just bumped into me. So at time two, C detects as a collision because they both sent a transmission, and it was at time around times one. So around time one. Sorry, time zero, and it was time one that they realized, hey, on route they realized, okay, something coming up, and then time two, the collision happened. So at that point, C detect the collisions, and then at time three, that message gets to time A, station A as well, indicating that, hey, a transmission from C come in this direction, got bumped into your transmission from A, okay, and that created collision. And when that happens, it's where the backup signal is sent across the entire given medium to hold off either D uh, or B from transmitting any of their information. Okay. So in the collision setup, an illustration of that, where the jamming signal is sent across after collision detected. Okay. A sending its frame on route towards B. Okay. Uh, maybe time zero, time one, two, or whatever time it is. B also sends a transmission, and before A could get to B, it receives that bang, um, collision. So you could say that this could have happened if, considering the time frame, A transmitted way earlier, okay, and obviously had enough time for B to detect that, hey, there was already a frame on the medium already before B actually transmitted. But as you pointed out earlier on, with voltage differences or surge, maybe B did not sense, because of voltage fluctuation or voltage difference, B did not sense that A had already transferred, the medium was already busy before it transmitted, and that led to the collision. And when that collision hits, there's that jam signal that's usually sent back to let A know that, hey, the frame you sent has got into collision, and that you need to back off. And if there are other stations also connected to the medium, it would also get that particular broadcast jamming signal, backup signal. So hopefully hold them back from transmitting information until the entire signal or the entire medium is cleared up again, or an idle time is sensed again before any of these other nodes or stations can transmit any information again or retransmit again. Okay, so this is how it walks you through the process using time-wise and other head informations. Okay, and here is a state diagram that basically illustrates the process of how some of these jamming signals are implemented, or the backup signal is implemented when there's a collision detected. So a packet could be a frame of packets, senses for a carrier, sends information when it's a collision detected. Is it yes or no? If it's no, it goes to the packet to resend it. If it's a yes, then a jamming signal is what? Basically activated. And the time frames allocated for clearance of the for clearing the jamming, for clearing the collision, and it has to be, an attempt has to be less than 16. Yep. So once it's less than 16 or attempts equals 16, then you decrease or you discard the packet. So in general, if a collision is detected, you introduce a jamming signal or you propagate a jamming signal within an attempt of less than 16 seconds or 16, whatever time it is. Okay, before you send a signal back to for retransmission or for sensing of the medium again. And in this case, if the signal is not or the medium is not jammed up, or collision is not detected, then you just forward information back and forth. So you have this routine uh, that the medium can observe to minimize or address collision need within collision detection, and the carrier sends multiple access. Very exciting stuff. A bit, over the head. Uh, but once you start thinking through it very carefully, you can easily start putting together uh, the concept behind some of these implementations. Okay. Okay. So within collision detection, the amount of time that it takes to detect a collision is usually no greater than twice the end-to-end propagation time. Frames should be long enough to allow collision detection prior to the end of the transmission. That is, it has to be shorter frames that must be used, and when collision uh, is detected, they are not in occurrence, or when collision is detected, those frames are basically discarded in a way. So hence, a frame should be long enough to allow collision detection prior to the end of the transmission. Then, if shorter frames are used, then collision detection does not occur. Okay, so that's in case you have frames of longer duration or longer length. For 10 to or 10 and 100 meg per second Ethernet, the frame length is usually at least 112 bits. For 1 gigabit Ethernet, the frame length is at least 4096 bits. And obviously using the carrier extension of frame bursting. So we'll look at some calculations uh, within that. And here we have, if an ISP was giving you 2 meg per second bandwidth, and it takes maybe 0.2 microseconds to transmit 1 bit, then a question, how much time would it take to transmit a full byte, which is 8 bit? Now, how much time would it take to obviously calculate that by using 1 byte equals 8 bits? Then obviously 1 bit should be equal to, if 1 bit is taking this much time, then an entire 8 bit would be what? If more or less device, right? With 1.6 microsecond. Now the other question is, how much time would it take to transmit 1 byte but at 4 meg bandwidth? So earlier you noticed that if it takes 2 meg to transmit a bit at 0.2 microsecond, then obviously 4 meg should take half the time if you do the math properly. Because now we have double the speed, right? So it has to be half the time now. So anyways, that's how we got the 0.1 microsecond. So we had the 0.2 times half the second, half the time. Can you see that? So 1 bit is 0.1 microsecond now. Initially it was 0.2, right? Now we have 0.1. So for 8 bit, you're expecting what? Instead of the 1.8, half of that is 0.8. So 1.6, you had 0.8. It's just half the time, basically. So simple calculations. Other ones, the same thing. A frame on a 10 meg bus takes this amount of microseconds to transmit 1 bit. If it took this, which is 2.07 microseconds to receive acknowledgement, for an actual transmitted data size of 128 bytes, then the question is how many bytes were transmitted within acknowledgement time. So in this scenario, you have 0.006 microseconds is to 1 bit. Then what is 2.07 microseconds is to? So cross multiplication, you'd have X would have about 345 bits, or 43.125 bytes will be transmitted. Determine if there was a collision or not, knowing the standard length of an Ethernet frame. This is a pretty good question. So in this sense, since an Ethernet frame is expected to be at least 64 bytes long, or equal to the size of data transmitted and acknowledged data size about 43.125 bytes, we can easily say there was some kind of collision during a 128 bytes data transmission. Because if you had to do the math properly, we did get going back here. Where is the standard? Okay, so yeah, so a standard data, also a standard Ethernet frame is expected to be at least 64 bytes long. That was a standard expectation within this scenario here, okay? And which happens to be equal to the data transmission or transmitted and the data and acknowledgement data size. And acknowledged data size is about 43 point this. In that case, we can say there was a collision. So based on the information you have from this calculation, you should be able to determine how much time it took to transmit the data as well as the acknowledgement of it, which in this sense was 43.125 bytes, because according it took this amount of time to receive information. Okay. So you could deduce there was a collision within that instance. Okay.